Let's start by reviewing what we learned last time about limits and continuity. The key idea is a function f defined near some number, defined near x equals c. So c is some unspecified number here, is continuous at x equals c. If what? What did we see? Well, we described it initially as you can draw the graph without picking up your writing utensil. That was continuity over an interval, say. We didn't want holes in the graph. We didn't want vertical asymptotes. We didn't want jump discontinuities. We didn't want infinitely many oscillations. How can you encapsulate not wanting all those things to happen at C? The limit should exist as x approaches C, for one thing. It doesn't exist when you have infinitely many oscillations of the same amplitude. It doesn't exist if you got a vertical asymptote. It does exist if you've got a removable discontinuity, but at the very least, the limit as x approaches C of the function should exist. And if we want it to not be a removable discontinuity, if we want the hole filled in, so to speak, it better equal the function value there. Okay? So that's the key equation for continuity at a point x equals c. It's a little strange when you think about it, because intuitively, when you think about drawing it without picking up your writing utensil, you're thinking about continuity over some interval. Is it possible that a function could be just continuous at one point? That actually is possible. Here's a weird example. Weird example. Do you need to know this weird example for the test? Maybe in a true-false question, I suppose. I wouldn't have you come up with this weird example on your own. Let f of x be defined in a piecewise way to equal x if, say, x is a rational number. What's a rational number? Well, fractions, ratios of whole numbers, 2/3, 14/5, -74/17. Those are all rational numbers. As decimals, they either truncate, like 0.5, or they have a repeating pattern, like 0.23, 0.23, forever and ever. Those are rational numbers. And let's let it be negative x if x is not rational. Numbers that are not rational are called irrational numbers. If x is an irrational number, which again just means not rational, this includes things like pi and e that have infinite decimal expansions that go on forever and ever without a repeating pattern. By the way, just because a decimal has a pattern doesn't mean it's rational, like this decimal. 0.0100100001000001, etc. That pattern is a pattern, but it's not a repeating pattern. The number of zeros keeps increasing. That's actually an irrational number. Just a little aside. What does the graph of this function look like? Well, you can't really draw it. The rational numbers, the decimals that have a repeating pattern or that truncate, densely fill in the real number line here, but there's still plenty of irrational numbers too. They densely fill in the real number line as well. So what do? Do I graph both x and negative x somehow at the same time? Kinda. I'm going to make a bunch of sort of like scattered dots along the line y equals x, and also make a bunch of scattered dots along the line y equals negative x. And I need to realize in doing so, I'm not really drawing the graph, and I didn't do a very good job over there. I'm not really drawing the graph. I'm just kind of imagining the graph when I do this. All these red dots have rational number coordinates. All these green dots have irrational number coordinates. Okay, I'm not really drawing it. I'm only sort of drawing it. And again, just imagining. This function is only continuous at one point. X equals 0. This is only continuous at one point, that point being the number x equals 0. Sometimes in calculus, we use the word point to mean number. In this case, that's what I mean. Only at one point, x equals 0. It's discontinuous everywhere else. The limit of this function as x approaches 0 is 0. It doesn't matter that it's sort of like oscillating between x and negative x as you approach 0. Those outputs, whether they're rational or irrational, are getting closer and closer to 0 as x gets closer and closer to 0. This limit exists and equals 0, and it does equal the function value there at 0. Because 0 is rational, well, I guess it wouldn't really matter. 0 and negative 0 are both 0. But as x approaches any other number, the limit doesn't exist. And I hope it's somewhat intuitive. You pick like the number 1. As x approaches 1 from either the left or the right, it's bouncing back and forth between two numbers that are close to 1 and negative 1, not a single number. So there are, yes, weird, wild examples. We saw a wild example at the end of class, sine of 1 over x, that oscillated infinitely often on Wednesday. They do exist, illustrating that our imaginations are somewhat limited when we try to think about when we try to think about calculus concepts with ordinary kinds of functions that we're used to. The function concept is broader. This is a well-defined function. No matter what the input is, I can tell you what the output is. It is a well-defined function. F of pi is negative pi, for example. F of 2 is 2. F of negative 17 is negative 17. F of e is negative e. Okay, I can tell you the output for any input. It's a well-defined function. Just a weird function. Does it have any applications? I don't know. I will talk about weird functions that do have applications. Sort of hinted at some last time anyway, but not now. What are some ways that this can fail? What are ways a function can fail to be continuous at a number c? Well, if x is non-zero, this is one way. Like again, I said, if x is 1, for example, as you get closer and closer to 1, the outputs bounce back and forth close to two different numbers, 1 and negative 1. What are some more typical kinds of examples where continuity can fail? I'm not going to write down formulas. I'm just going to make some pictures. One way we've seen continuity fail is if you've got a removable discontinuity. Maybe the graph looks like this. This is x equals c. If your function looks like this, and maybe the function's not even defined at c, you could say the limit as x approaches c of this function exists, but it doesn't equal the function value because the function value is not even defined. F of c is undefined. Okay, well, let's consider a new example. Maybe the same kind of thing, hole in the graph, but let's define the function at c. But it doesn't equal the second coordinate of the missing point. Maybe this is 3 and this is 4, just to pick some numbers. There, the limit as x approaches c of f of x exists and equals 3 in particular, but it's not equal to f of c, which is 4. Okay? In both cases, these are removable discontinuities. Removable discontinuities at x equals c, because I could easily redefine the function so that they're continuous at c. Whatever the second coordinate of that point is, I could say f of c is that second coordinate. In this case, I could say f of c is 3 instead of 4, and I would have removed the discontinuity. And again, like I mentioned last time, we're going to see for sure next week, these are not mere curiosities. This happens with derivatives all the time. In fact, every derivative you calculate, you end up dealing with a function, not of the original variable x, but of a new variable called h that has a removable discontinuity. All right, what are some other ways a function can fail to be continuous? You could have a function that's defined everywhere, including at c, but maybe you've got a jump discontinuity like that. The function output jumps in an instant. When x is just barely less than c, maybe the function outputs are approaching 3. When x is just barely right of c, the function outputs are approaching 4. Here you can say the two-sided limit doesn't even exist. So there's no way that this equation can be true because this is implicitly a two-sided limit. I'm assuming f is defined near c, meaning on both sides of c. In that equation, this is implicitly a two-sided limit. There's no plus or minus to the right of the c. I can see I've got one-sided limits here. The limit as x approaches c from the left, by how I've drawn it, is 3. But that does not equal the limit as x approaches c from the right. Negative sign to the right of the c number means you're approaching c from the left. It doesn't mean through negative values, and I've drawn c to be positive, in fact. Plus sign to the right of the c means you're approaching c from the right. These are called one-sided limits. They do exist in this case, but they're not equal. And that's enough to say the two-sided limit does not exist. Limit as x approaches c without a plus or minus sign to the right of c does not exist. Because in order for that to exist, the one-sided limits must exist and be equal. Is f of c defined? Sure, it is defined, it equals 4, because I filled in that dot there. But that's irrelevant. The two-sided limit doesn't even exist, so the function is not continuous at c. I could have filled in the other dot instead, and then f of c would have been 3. There is a notion of left continuity versus right continuity. This function is right continuous at c because f of c equals the right-hand limit, but it's not left continuous at c because it does not equal the left-hand limit. I'm just mentioning that. We're not going to focus on one-sided continuity in this class, okay? Just briefly mentioned it there for the last 30 seconds. But yes, this is called a jump discontinuity. Are there other ways functions can fail to be continuous? Yes, we've already seen them. You could have a vertical asymptote. I should use red here. Your function could have a vertical asymptote at c. We've typically drawn functions with vertical asymptote where maybe it goes to plus infinity on one side and minus infinity on the other. But it can certainly happen that it goes to plus infinity, for example, on both sides. In this kind of situation, we have written the limit as x goes to c. And in this case, since it's going up forever and ever on both sides, it would be a two-sided limit. We would write plus infinity here, equals plus infinity. But I have emphasized, even though that we write this, infinity is not a number. This is just shorthand notation to say the graph goes up forever and ever, gets above every horizontal line, no matter how high it is, as long as you get close enough to c. So it can't possibly equal f of c, because infinity is not a number. I guess I haven't defined f of c, but I certainly could. Oh, maybe f of c is 2, but that's irrelevant. Infinity is not a number, so it doesn't equal 2, which is the function value at c. And yeah, I could have also left f of c undefined. Any way you think about it, it's not continuous at c. And then we also have our example, sine of 1 over x in particular, we saw oscillates infinitely often with effectively constant amplitude of 1 as x approaches 0 from either side. This function doesn't approach any particular number. It oscillates between -1 and 1 infinitely often on any little interval around 0, no matter how small it is. I could even define f of 0 to be 0. I could make it a piecewise function. That's irrelevant. The limit as x approaches 0 of f of x does not exist. And you can't even say it equals plus or minus infinity. It doesn't have a vertical asymptote. Let me go ahead and use the formula here. Let's just go ahead and pretend this is the function equal to sine of 1 over x if x is non-zero, and I'll go ahead and define it to be 0 if x is 0. I could define it to be anything I want if x is 0. It doesn't matter what I pick, it's still discontinuous at x equals 0 because this limit does not exist. Do these kinds of examples show up? Yeah, they could show up in some ways on homework. They could show up on exams. You should spend time thinking about these. Is this the only kind of function that oscillates infinitely often? No, there's plenty others. In fact, you could say there's infinitely many examples of functions that oscillate infinitely often in your points. Yes, they are weird. You might say they don't have applications, but you could be wrong there. They might have applications. And we'll, again, try to hint at some applications of weird functions, probably in chapter 2 at some point. So continuity at a point is related to limits. So we need to understand, that's one reason to understand limits better. So far, we've tried to understand them intuitively in terms of graphs. We want to try to understand them a bit better today. Limits are also very important for derivatives. And limits are also very important ultimately later in the course for integrals. In fact, the limit concept is what separates calculus from plain old algebra. If we're using the idea of a limit, that's where we pass beyond algebra into calculus. Continuity, derivatives, integrals, it's also relevant to something called infinite series that you'll learn about in calculus 2. And all those things as well, derivatives, integrals, series, they can be generalized even to higher dimensions. And matrices, you can have infinite series of matrices. You can do integrals in higher dimensions. So it gets really, really wild and yeah, pretty challenging, but pretty interesting as well, I think.